Thank you so much. Thank you for inviting me. And up until previous talk, I thought that mine will be the most nerdy, but I cannot beat Dr. Stein in it. My name is Olga Kononova. I'm a research investigator at Roivant Sciences, and I have math background with a little bit of chemistry and physics. So, I will also have a lot of formulas, but please do not hesitate to ask me questions. As I mentioned, I work at Roivant Sciences, and at Roivant Sciences, I work at the Roivant discovery part, where we focused on the discovery and development of the drugs at preclinical stages. And this is the typical pipeline that we use here, and it involves target selection. It involves target selection, then choosing of the lead compound, optimization of that compound, and the preclinical tests. So we use both the computational and experimental approaches. And aside from the people in our group who work on the creating the new drugs, we have also people who develop the model for those people who will be creating the new drugs. And I belong to this kind of team, and I will tell you today about my favorite part of this pipeline, which involves molecular dynamic simulations. I will tell you a bit why do we need it, how we use it, and specifically my perspective on it and where it should be developed further. So why do we care about molecular dynamic simulations in drug discovery? So when we talk about the efficient drug, actually that active ingredient that you usually see on the medicine that you buy, we talk about the little compound, and if we want to know how optimized it is, if we want to know how well it will be binding to our target, we talk about the measure, which is the binding free energy. So in Roivant discovery, we found out that whenever you measure you can screen the drugs and do the experiments with them, and then what you find is that without using any prediction or tools, in a cycle you can make around 50 designs, and then you come up with some drugs that you think might be working, but then most of them will be inactive. So as you can see here, that's without using any computational filter, most of your drugs that you predict that they're supposed to be good drugs are actually inactive drugs. So what we used is we used this binding free energy filter, which allows us for the cycle to have almost 700 drugs for designing, and then from them do selections, narrow down the selections, and this selection allows us to have more accurate prediction of which drugs are more effective and create this prediction in order to have more optimized design. And with this, we can significantly reduce the amount of the cost of the drugs production and also the amount of work hours. So we have more vacations because of that. So the most important part here is that as more accurate is your binding free energy calculations, as less redundant work you will be doing, as less money you will be wasting, as more careful will be your prediction. So we do care very much about having the binding free energy calculations to be accurate. For this, we need molecular dynamic simulations. And today I'm going to talk to you a bit about, I will give you a primer into molecular modeling, what it is, what is the problems there, what are the main challenges in the creating of the force field, what is this force field, and I will tell you more how we think about the shifting the paradigm of representing the atoms and chemical environments toward continuous representation, atomic embeddings, rather than the tabulated way that it existing currently. So what do we actually mean when we talk about the molecular dynamics? Yeah, we mean the jiggling of these atoms. They do not jiggle randomly. So for every atom here, we do solve the second Newton law equation. And for every atom, we basically can calculate the position. We can calculate the position of the atom. So it's here. And it depends on the change of the energy. On the left side, you have coordinates. On the right side, you have your energy. So with this, the most important is, in order to propagate your coordinates, in order to get the coordinates, you need to know the energy. And this is the whole game. So you have to know how to calculate this energy, which is on the right-hand side. There exists an enormous amount of techniques how to do it, from the most accurate, which is quantum mechanics, to the least accurate, which are coarse-grained and the mesoscale computations. So quantum mechanics is usually the most accurate, but unfortunately very computationally costly, and it's mostly used these days in order to provide the data set which will be used in order to parameterize less accurate but more computationally efficient molecular dynamic simulations, MD. Coarse-grained is also one way to have this to speed up computations is when you consider not necessarily one atom but all common center of mass which represents the group of the atom. I'm not going to talk today about it. I will tell you more about molecular dynamic simulations, which is we use a lot because it's enough to be accurate, and yet you can reach the biological time scale when you see the binding events, when you see the transformation of the structures and so on. So, as I said, molecular dynamics, it depends very much, the way how you, classical molecular dynamics has its own way to define this energetic function. So this E here is the force field. So whenever I say the word force field, you should refer to this equation of motion to the right-hand side, your energy of interactions between the atoms. Oop. That's it. Okay, now it works. So what is actually the force field? What it includes? So here you see the simple molecule. It's a simple molecule, trust me. So when we talk about the force field, we talk about the different interactions. We talk about how our bond between two atoms stretches. We talk about how the bond rotates. How the bond rotates, so we talk about the angle, in planar angle between three atoms. We talk about the torsion energy, so how you have the torsional rotation of the part of the molecules. We also talk about the non-bonded interactions as the electrostatic interaction and the between the charged atom, and we talk about the non-bonded interactions due to proximity of two atoms together. So this is the very much approximated and very much simplified version of the classical molecular dynamic simulation. That E term is basically a combination of all these terms, and each of these terms has a lot of parameters, which depends very much on which exactly atom we are talking about. So for these purposes, in order to parameterize each of these functions, people created the approach that used so-called atom types. So briefly what it does, you have, based on the chemical environment where your atom is embedded, you can define the atom type and assign it with the specific parameters. In order to identify the values of these parameters, people usually use the quantum simulations in order to fit it. Now think about it. You have several terms at least, not counting many other terms that will make your potential to be more accurate. Yet on top of this, you might have a lot of, you might have the different atomic environment, and you may have, as the result, different atom types. The parameterization problems can become really unfeasible. And just to prove it to you, we can, so you can see here on this slide is that these are only one carbon atom. It's the same carbon atom, number 14 in the periodic table maybe, but it's embedded in a different environment. So it's an environment as the ring, it can be an environment which is outside of the ring. So all this same carbon will have seven different atom types, and it will be having several different parameters. And the associated potential will also have several different parameters. So for example, you can see here the charm and the amber, one of the most used force field models in molecular dynamic simulations. These huge teams of people, they've been working on development and parameterization of the force field for decades. They invent more and more atom types. They try to parameterize it more and more accurately, but we're still there. We still have a lot of situations when the parameterization doesn't work, and we have to come up with any workaround. So this approach with the atom types, it's been here for years, but the question is, do we really need it? Because the first limitation is that this is the rule-based approach. So the way how you define the rules, the way how you say that your atoms are, atom types are defining the environment, This is the way how your model will be parameterized. As the result, if you talk about two different models, transferability between them is almost impossible. The second problem is that for this small molecule, you can come up with a solution which will fit the parameters, and you will have more or less accurate molecular dynamic calculations. But if we would talk about the huge systems of the hundreds of thousands of atoms, parameterization becomes clearly unfeasible, and it's really almost impossible to create that many atom types that will describe every possible chemical atomic environment. Lastly, one of the biggest problem here, why do we think that the atom types does not make really your calculations to be accurate? Because you can be as accurate as the amount of atom types that you have. So you may have 2, 3 atom types which define your chemical environment, and you can have a perfect parameterization, fits perfectly quantum data, but it won't be able to properly describe your system just because your system has way more options for the chemical environment. So then the question is, do we really need these atom types? Do we really need to take our continuous chemical environment, squeeze it into the tabulated atom type environment, and then from then go back to the continuous mechanic, or to the continuum environment? So there is actually a very interesting observation is that one of the most, masterpiece of the paintings are the ones which preserve most of the information. So in this context, we also think that maybe we don't need really this discretization of the atom types, and we can really keep going with the continuous atomic representation when we go from our system, when we go from our structure of the molecule to the parameters of the force field. And the question is actually yes. So for that, we have done some work on building so-called atomic embeddings. This work is based on the graph neural networks, and I'm pretty sure most of the people here are familiar with this, so I'm not going to describe the concept. But what we have done was the following. So we take the molecule and we assign it to the graph. So the graph has the nodes which corresponds to the features of the atoms in the molecule, and the bonds correspond to the features of the bond in the molecule. So usually it's your features of the atoms will be the element name, the periodic and group table, in the periodic table, hybridization, formal charge, and bond type. There is so-called different types of chemical bonds, so that's what we include in our work. Then we pass it through 3 layers of transformers, the graph transformers, and train it against and then the embeddings get trained against of the classification task, which is defining the atom type. We used our own in-house atom types, which were about 500. So we played a little bit with the different architectures, number of layers of transformers, dimensionality, and we used the That's it. No. And we use around 2 million of molecules to train this model. And we use the standardized drug data set in order to test. So these are not overlapping data sets. And what we can see is that our model actually performs pretty well, if I can switch to the next slide, of course. Right. So our model performs really pretty well, and it's the accuracy here which is shown is the accuracy per molecule. So it's not that it calculates if the atom was correctly assigned with the atom type or not. It defines if the whole atoms in the molecules are assigned correctly with the atom type. And if it is, then it's correct. If at least one atom is assigned incorrectly, it's not correct. But assigning the atom types and predicting atom types is not the point here. The point is to see if the embeddings that we created actually can reproduce anything. And that they actually can. So we did some analysis here. We plotted the 3D representation of the embeddings, the PCA components of the embeddings, and color it in a different way to see how they get clustered. And what you can see here is that actually these are just 2 snapshots. I couldn't show the whole visualization of it, But if you take, for example, nitrogen, all the nitrogen atoms, and you color the embeddings according to the amount of neighbors that they have, what you can see is that it nicely clusters separately the atoms that have only one neighbor, only two neighbors, three neighbors, and four neighbors. You can also cluster the ions, and what is cool here is that so the different color corresponds to the different elements. But these are green clusters, they both correspond to the sulfur. The fact that these two clusters are separately corresponds to the different types of ions, the sulfur with the valency 2 and the sulfur with valency 4. So there has been some more analysis done on it, but we can clearly see that our embeddings that we train can pick up this environment, the chemical environment information, the hybridization of the atoms, the amount of neighbors, the connectivity, and everything else. Right, so the next what we tried to do is next what we tried to do, we were thinking, can we actually do that that step when we predict directly the parameters of the force field bypassing the atom types and going directly from the structure of the molecules to the parameters. And we tried predicting the reference bond angle and the reference bond length. So this is the B0 and theta 0 factors here. Right. And for these purposes, we constructed the neural network, which two neural networks. We constructed the neural network in a way so it represents the function that is invariant with respect to permutation of two atoms. So you want to concatenate A atoms I and G, and your prediction will be exactly the same as if you concatenate G and I. And the same for the angle. So the reason why we also choose to predict this specific parameter is because we have the experimental data for this, the crystal structure experimental data, and that means that we do not depend on any model and any approximation that can be induced or any bias that can be induced with this model. We trained on crystal structure from the Cambridge Crystal Structure database, around 24 million of bond values and angles values, and we tested the results against the currently existed molecular modeling packages. We choose so one of the tests that we have done was to choose to use the molecular force field to optimize those experimental structures that we use for training and see what is the difference between the prediction of our model and prediction of the molecular dynamic package. The other was we use we choose completely different set of molecules, optimize them with the quantum mechanics computations, and then compare it with the prediction of the model. To save the time, I will skip it, but the resume here is that our model works at least as good as the quantum mechanical prediction, but yet it's faster because you don't have to do the quantum mechanical prediction anymore. You can directly go from having the structure of your molecule, predict the parameters of the molecule. And the same for the angle parameters. So one of the most important things that we achieved with these atomic embeddings was that we could bypass this discretization of the atomic environment. And this is crucial for the situation when you describe electrostatics. So when you describe electrostatic and interactions between two atoms, you will have this, you have to know the charges of two atoms. So this problem has been, the best solution that exists right now is restrained electrostatic potential, which is absolutely slow and very unfeasible computationally. So we have done the approximation which takes the charge and represents it as the sum, the nominal charge and the correction term. So the correction term is consisting of all these partial charges that get the distortion basically of the charge of every atom. I'm really sorry for this, it just doesn't go along with this. I'm pressing the button and it just doesn't respond. Right, so what you can see here is that the task here is that you need to know this P1, P2, how much of the partial charge is transferring from one atom to another atom depending on the atomic environment. So you can, in principle, create the table and try to fit this table, But what will happen is that for every new molecule, this table will be different. The table of the parameters will be different. For this, that means that basically using the discrete atom types doesn't make sense anymore. But we can go directly and use the embeddings here, so bypassing these discrete atom types and tabulation. We have done it, and we found that our model, actually performs even better than tabulated atom types, but almost as good as the state-of-the-art restrained electrostatic potential model. On the other side, as you could see probably from the previous slide, is that the restrained potential will take around 50 seconds per 100 atoms to calculate it, while the model which we use takes less than 2 seconds per 100 atoms to calculate it. So the most important to take out from there is that you can quickly produce as accurate as the standard parameterization, the values of the force field. But on another side, it is as accurate, but it is bypassing this rule-based approach. And what we really hope is that this will be the first step when people start thinking, do we really need this tabulation of the atom types? And right, so let me jump to conclusion, because I was also notified that I should really be quick on my talk. And so we need the accurate force field parameterization, because we want to have the accurate estimation of binding free energy, which we will be used in order to identify what are the most promising drugs which we want to explore in the future. So fitting force field parameters is the really very difficult task. If we want to make it accurate, we have to really spend a lot of effort on it. The way how it's done right now, it's using this tabulating of and rule-based creation of the atomic environment. Is it good? No. Is it used by a lot of people? Yes. But it is computationally not always feasible to create all the possible rules for any arbitrary molecule, although for the groups of molecules as proteins and lipids, they has been already brought to the perfection. But since we are interested in drugs, and drugs are very arbitrary molecules, and on the current stage that we have, the number of the drug molecules increased significantly with the time. So, and with the invention of the generative models, we also expect that the number of the potential drug molecules will rise significantly in the future. For that, creating the procedures which will require manual fitting of the parameters, of course, doesn't make really much sense. And tabulate all the possible environments also seems to be impossible. So we believe that continuous atomic embeddings, continuous presentation of the atomic environment is the step to make towards the new development of the molecular dynamics models. And we also think that this is one of the ways to reduce the human bias that gets introduced in all these models. So we think that giving the information about the molecule structure, which allows it to pick only the most important features for creating the parameters, rather than go to this rule-based approach, which is very much artificial. And we're happy to see that already the academics group doing the step forward toward this development. And one of the prominent examples is Paloma package, which allows you to bypass these discrete atom types and go directly to the prediction of the parameters exactly from the structure of the molecule. So with this, I really want to thank the whole group with which I work, which is led by Chuanji Wu, and special credits to Sebastian Dick and Rahul Ravi, who helped a lot with these results. Sebastian worked on the charge model, and Rahul was working on the QM-optimized structures. And right, I will be happy to address the questions.
Thank you. Thank you. Wonderful. First of all, great job. And this was in a very short time frame. Yes, great job. Also want to thank you, on behalf of all of us. The fact that we're, able to have this event in person is because of this drug development. So we do appreciate it. And thank you so much for your talk.